let's examine integral 0 to pi, that's x from 0 to pi, and y from 0 to pi over 2 of sine of x times cosine of y. Now, we're not going to actually do this problem all the way through. We're going to just use this problem to really talk about kind of a neat technique that can sometimes apply. Let me highlight the inner integral, and in what's in yellow, if we just focused on that, it's a dy, so x should be treated constant. Well, if x is constant, sine of x is constant, so you could bring that sine of x outside of the inner integral, and it could look like this, right? So integral 0 to pi, sine of x was it was considered a constant as far as the inner integral that's inside the parentheses is concerned, since that inner integral was treating y to be the variable. But then take a look at what we have here. Even if we don't do the integral in parentheses, look at integral 0 to pi sine of x. If you look at this integral 0 to pi over 2 cosine of y dy, all of what's in there, we got real lucky that there's no x's in there. You could just pass this off to a student in Calc 1. Integral 0 to pi over 2 of cosine of y dy. If they're really freaked out by the y's, just switch all the y's to u's for them for a second or something like that. The whole point is that they should return to you a number. What's in parentheses already is just a number, and you can just bring that. Okay, so here's what it actually is. It happens to be the number 1, but who cares what number it is? The point is you can actually bring that number here, even without computing it. We just know it's a number. Bring it in front of this integral. Bring it in front of the integral of 0 to pi of sine, and so on and so forth. So when you do that, this entire number, I've just pushed this thing in front of the integral that has the 0 and pi written on it. In the end, what we actually have going on here is the original integral that was at the top ends up just being the product of two one-dimensional style integrals. Instead of this two-dimensional integral, so to speak, we actually just have the product of two separate one-dimensional integrals. So the double integral became the product of two single integrals of different variables. And this is an example of the following. So if you have the situation where f of x comma y is written as the product g of x times h of y, then your double integral can be split up as the two separate integrals. So for example, in the first example we looked at for the day, x cubed y is a product of independently the x cubed times a y. So we could, this y this y belongs over here. It could be integral 3 to 8 of y dy, and then integral 1 to 5 of x cubed dx. Example from earlier, you were asked to integrate the function y times sine of x. Again here, you can split this up as a product that separately mentions y's from x's. So you could split this up as an integral of y from -1 to 6 and multiply that result by the integral of sine of x for x going from 0 to pi over 2. Interactive question, why would it be incorrect to split here though? If you had integral 0 to 4, integral 0 to 3, x squared plus y squared plus 1 dx dy, why would it be incorrect to split this one like this?